Okay. So actually, I wanted to wait for Eretz because I now have an answer to his question. I figured it out. But maybe, okay. Okay. Okay, so Eretz, I have an answer for your question, I think. So for example, this with the exact okay. So if I look at a model state, so imagine they take how do I build model states of FCIs? I take the Wannier basis, which is kind of Landau gauge in one direction, and I just look at those single particle orbitals and give the same weights of the Slater determinants as in the Laughlin state. For example, that's a model FCI state. That state will certainly have the occupation of that orbital to be exactly 1/3. So there should be a basis where the occupation is exactly 1/3. For example, the Wannier basis would be one of them, right? Maybe not the initial basis of the single particle states, but at least right, the way we build model states for FCIs, at least back in the days, was you just take the Wannier basis, which is the Landau gauge, and you use the same occupations as in the FQH states, and then you're guaranteed to have the 1/3. So I'm not sure how that goes back if you put it into the original basis, but at least in some basis you should get something. I think that's my. Well, I don't know if that's a. But I just thought of that as I don't know if that satisfies you, but I think we can talk about it later. Okay, very good. So let me just explain some of this plot. So basically, I said that pentalayers gives you, k plus ik to the fifth or to the nth. Okay, but this is a gapless spectrum. The spectrum looks like this. Okay. And actually, Moiré, forget about Moiré now, in order to open this gap here, I need, which is what you see here. Here you see many things. There's folding, there's the Moiré scale, not the original scale. This is the original graphene. Here I have the graphene momentum. This, you can see it here, is just some folding of this, at least in the conduction band. But you see also this large gap. Sorry, go ahead.
So that band structure you're drawing is basically you take 5 layers and then you couple them in the Z direction.
Exactly.
And don't impose any more, right? Just the Z.
ABC, though. ABC.
Okay,
it would be a bit different for AA.
Okay, ABC stacked.
Exactly.
Couple them in the Z direction.
Exactly.
The bands in the Z direction.
Exactly. Very good. Exactly. And then you can put a displacement field, and then you open this gap. And this is this gap, and the displacement field just corresponds to putting for 5 layers, 2 times V here, and minus 2 times V, and 5V is the potential. So the gap here would be 4V, okay? This is 4V. At k equals 0, I have a state at 2V and one at minus 2V. That's the displacement field between the lower layer and the upper layer. I have 5 layers, so minus 2V, minus V, 0, plus V, plus 2V. And that creates this gap, okay? And this is the role of the displacement field to create this gap. Now, k to the 5th, as you can see, for small k, is very, very flat. But at some point, and we know what that point is, the dispersion shoots up. So I'm not sure if Eve is here. We have a name for this dispersion that we're going to publish soon, but I won't tell you the name. But basically, it has a very interesting characteristics. So now you add displacement field, it would look like this, with this being 4V. Okay? So, and then you can fold it and it starts looking like this. Here, but not here. So let me give you a little bit more of really what happens. So this is with and without relaxation again, but basically, as you can clearly see, the relaxation only matters in the, this is ab initio, but it only matters in the valence bands. The conduction bands are basically the same with and without relaxation. So you see this k to the, at zero field, you see this k to the fifth, and then you add field, and there's a gap induced by the field, and a flat band here. Now this flat band here is just this flat band of the unrelaxed, of the unmoiré twisted graphene plus folding. And this band here, you can see gaps here, okay? So if I just had this band, if I just had the lower band folded, I wouldn't see gaps, right? I just fold it. It would be like this band folded. You know, if I fold this, it would be like I would fold it, and I would see many things exactly like here, but this one would look the same, but it doesn't. And the reason is that this one feels the moiré very strongly, and moiré opens gaps. So you fold it, and then you open gaps, and when you open gaps, once I fold it and open gaps, things can change. So why does this feel the moiré strongly and this doesn't feel the moiré strongly? Well, as I said, the HBN is only, the system is twisted and aligned. It doesn't matter if it's, I mean, it does matter that you get a different periodicity, but even if you didn't twist it, you still have, if it's aligned with boron nitride, you still have a moiré, only on one side. The other side is unaligned. So we're just going to forget about the other side, and we're just going to remember that it's aligned to one side of the moiré. So, in order to understand why the system feels, why one of these flat regions feels the moiré strongly, the other one doesn't, you just write down the wave function. This is what, you know, Vidya was pointing out. There's just really a system which is, looks like this. So let me write down for pentalayers the Hamiltonian of no moiré, because you can understand everything from no moiré, okay, so far. Not, the hard part happens in the interactions. So you have, let's call it K minus K plus, right? This is K minus, this is K plus. This is one layer, but then the rhombohedral stuff has, this is the unit cell. The next unit cell is like this. Okay, the next layer is like this. So you only have hopping between the A of one unit cell and the B of the other, of the next layer, okay? So if this is A, B, A of first layer, B of first layer, this is A of second layer, B of second layer, A, this is my basis, then I'm going to get, you know, the uncoupled Hamiltonian is K minus, K plus, 0, etc., right? That's just A3, B3 of the third layer, 0, K minus, K plus 0. But then you're going to get this coupling between, the A and B. So this is A1, B1, A2, B2, etc. So you're going to get some T terms here, T perpendicular. Okay? Those are just going to be your terms. And then you're going to get a T perpendicular here. And of course, this has to be Hermitian conjugate. So you get some T. And this is just the hopping between the A and the B out of plane. So then you can immediately see there's a low energy wave function. There's two low energy wave functions. And they look like this. One of them is 1, 0, K minus. There's a VF, obviously. There's a Fermi velocity here. So let's do VF K minus over T. 1, 0, minus VF K minus over T. 0 minus VF K minus over T squared. 0 minus VF K minus over T to the third, all the way to the fifth, actually to the fourth in this case. And the other wave function is exactly the opposite. 1 on the fifth layer. You see, this is constant. 1 on the fifth layer, 0, K plus over T VF, I think, to the first power, then 0 minus VF K plus over T to the second power, etc., 0. Okay? Those are the wave functions. You can immediately see that these will be very good. They're actually not exactly eigenstates. There's a little error. But for the region VF K minus over T less than 1, these are very good wave functions. And they get even better as the size of the number of layers goes large. Now, where's this thing? What's this? This is just this momentum. This momentum is basically VF K minus over T is equal to 1. The bands are flat. They start shooting up at this momentum. So for this region, and this is true even for the bands that, even for 0 displacement field, for this region, for this flat region, you can just solve this. This is simple Hamiltonian. You can just solve it. For this region, the bands look like this. So now look where they're localized. This is the band at positive energy, localized away from the moire. Most of the way to see it's an exponential decay. If this is less than 1, then this term becomes small very fast. Okay? So one of them is localized away from the moire on the upper layer, and the other one, which is the valence band at -2, that goes to -2V once I add this potential. So this, once I add this potential, this becomes 2V, this becomes -2V. This one is localized towards the moire, and that's why it feels this effect strongly here, the moire effect strongly, and opens gaps, etc. So moire potential is important, and I haven't described the moire potential here. But understanding why these bands up here don't care about the moire is just the fact that in these pentalayers, or in any n layers, you have an energy, you have a momentum scale. This momentum scale is given by VF K over the T perpendicular, the hopping between the layers in the Z direction equals to 1. Everything for K lower than this, the bands will be flat, okay, because they'll actually have dispersion, K to the 5th, okay, times VF over some T, etc. So K to the 5th is very, very flat up until it reaches some scale, it starts shooting up. And then the wave functions for this VFK over T less than 1 they have basically a sequence that's decaying exponentially. For one of them is decaying as you go towards the moire. So the weight of this wave function on the moire layer, which is low here, is very little. You see, it's VFK over T perpendicular to the 5th power in the end, and that's very, very small, to the 4th power, whatever, some power that I could figure out. But if this is less than 1, and this number is about 0.6, actually, in the moire. So the moire scale, if I plug in the moire here, K, this would be about 0.6. So 0.6 to the 5th, it's very small. So so these electron bands don't feel the moire. They actually feel the moire to less than 0.1%. In other words, the change by adding or not adding the moire is 0.1% in the wave functions. Whereas the valence bands do feel the moire.
Question, in your Pentalayer model, do you have only one hopping between layers and not some kind of longer range?
Yeah, but I mean, this has to be the strongest hopping, because this is right. This is A, B of the first layer, and this I move it up. So you have A1, B1, A2, B2. So it sits right on top of the other one. All the other hoppings are longer ranged, so they have to be smaller. And in ab initio they're much smaller actually. So basically, because this is graphene, the hope is that one can actually model things very well. So with very simple models, you can match at least the ab initio, which is very complicated actually. Ab initio is, but you can match these. These are actually on this slide. These are actually models with very few parameters, not exactly just one parameter. We have some trigonal distortion, etc. here, but you see the fitting is very good. So is it clear about what's towards the moray and what's away from the moray, and why the conduction bands don't feel the moray, but the valence bands feel the moray? If it's not clear, tell me, but if it's clear, yes?
If the folding, if it doesn't feel the moray line so strongly, then what about the folding?
Then why am I folding? Yeah. Very good question. Yes. So that's exactly the point of the next part of the talk. But that's exactly the point of yeah, so that's exactly the point. Why am I folding? If they don't feel the moray, why not work in the original, right? The reason is that you do see a churn 1 state, integer, right, in the experiment, at filling 1 of the moray unit cell in the conduction bands. So that's the puzzle. Conduction bands don't feel the moray, at least in single particle. Now, with interactions, that's where the controversy starts. So at least in single particle, they don't feel the moray, but you do see an insulator with quite, a sizable gap and, well, what should be a sizable gap and 0 RXX, an integer churn insulator at fitting 1 when you sit somewhere here of the moray. So why? So is it clear what the puzzle is? Or maybe not? So this is what I was telling you before. So basically, I'm going to skip. I thought I could go through many details, which, it's always a fallacy, to overload slides. But I'm going to neglect some of these details, so don't read everything on the slide. Actually, read nothing besides what So basically, this is what I was telling you before. This is k to the n dispersion plus minus k to the n for 5 layers. Then you have this n-fold vortex, but then the wave functions are either peaked here or peaked here. One of them feels the moray, the other one doesn't feel the moray. There are some relaxation things that you can see. Now, it's not like in the moray side you don't see fractional churn insulators. There was a paper, I think also yesterday by Ray Ashuri and Long, that they require a little bit of field. For example, it's filling 1/3 on the moray side, you require 0.2 Tesla to get to sigma xy equals 1/3. So, these phase diagrams, right, now they have like so many knobs, they're very complicated. But the moral of this, the interesting and the first remarkable puzzle is you've got a gapless band structure. Why fold it, like Menk was saying? But you see an insulator, and by the way, this is per valley per spin, so I've already polarized valleys and spins. Okay? So I'm just working basically by many-body effects. So actually, this you can kind of understand because this is a flat band, so it likes to polarize valleys and spins. I think Pivy talked about it, and maybe errors too. Yes?
So filling the moray to 1, which is putting 1 electron per site.
Per moray,
Site.
yes, per moray unit cell.
If you didn't have the moray, that would be some small fraction of that band, some tiny.
No, that would be basically this. This is a small fraction of the original graphene band, right? So this is the K point of graphene. This is the M point of original graphene, not moray. So you see, this is a very tiny region that is flat of the original moray point. But this would be basically the same energy. It turns out, so all these moray physics, and this is similar to Andrea Young's experiment where there is no moray in bilayer. There's always a length scale in the problem, and the length scale in the problem is always of the order VF. There's T over VF, T perpendicular over VF. And if you look at this length scale, it's around 10 nanometers. The same thing as the TBG moray, the same thing as if you rotate. You see, even if I didn't rotate this guy here, if I didn't rotate the boron nitride, I still have a moray because they have different lattice structures. That length scale of that moray also around 10. I mean, 14 to 10. But they're very similar. So in all these problems, there's a length scale.
So you basically fill that flat
Exactly. You'd basically fill up to that's roughly what I see the filling one churn.
But then could it be that the valence band, the conduction band doesn't feel a moire and you're filling the flat band partially?
Well, but it's a gapless band, you see. So you could, so the question is what gives you a gap, right? And even an integer filling. The question is what gives you a gap. So
Correlations.
right, sure, but why this filling?
But if you have a peak in the density of states and you partially fill it,
If I partially fill this band, sorry, so you want me to partially fill this flat region or partially fill, right, so so the churn insulator is filling basically one of this flat region.
so fully filled.
Sort of. So basically I'm just at the interface, roughly, at the interface of this flatness to this jumping up. And then you fractionally fill that flat band and you get, this FCI states. Very different from Landau levels, clearly, right? By the way, this band here has almost constant Berry curvature up until it's almost constant. So you can work out the details. It has almost constant Berry curvature. It doesn't add up to 1 because there's no gap in the system. It adds up to actually one quarter. If I would compute it's a metal here, right? But I can still compute the Berry curvature and integrate it up until some momentum. And that would give you 1/4 of 2, 1/4, it wouldn't give you 1. Okay, more questions? This cannot be that obvious, so there's got to be questions. Or if there's no questions, I'm basically explaining poorly.
I guess on a related thought, I forget, there's also experiments where they don't have the boron nitride, and how different is it there?
Right. So there's very recent experiments, like 3 days published, right? Where they don't have the boron nitride, they don't have the moire, and they don't see the sigma xy equals, they don't see the churn insulator. But then if you press, so I just pressed a little bit long on it at this KATP conference, he says, there might be, it's a huge region of parameter space, right? So he says that, there might be regions where you see it. But this anomalous Hall crystal that I'm going to be telling you about now is, not seen in. So now that paper is published. They don't see it in untwisted, unaligned actually, not even untwisted. So the moral of the story is basically, what's the moral of the story? That Long would say we haven't looked at the entire phase diagram, which is always, with so many tuning parameters, always something that should be kept in mind. Okay. So basically now we're getting a little bit more into theory land, but this is kind of important in order to try to explain things. So this is a gapless state. It's a metal without interactions, so you got to put in interactions. So there's many ways of adding interactions, but there's basically 2 main ways of adding them, which would correspond to either this gap being super large or this gap being super small. Now, semiconductors have this gap 1, 2, 3 electron volts, insulators, etc. Metals have this gap 0. This is about 30 electron volts. You be the judge of what's small or what's large, right? So, we don't know whether these 2 types of interactions, one of them we know that cannot be correct in the small gap limit, but we don't know if the other one overestimates some tendencies, etc. So what our team has done is to analyze both these type of interactions. So let me tell you what you do. And this is a common theme when you add interactions, that basically you got to make a choice, which is called the subtraction scheme. So basically what you can do if this, and this is what people, Nicolas and Eve, I think, spoke about it, what people do in TMDs. TMDs have a huge gap, okay? And huge single particle gap. and then you fill up some valence bands, and then you ask, what's the interaction as I fractionally fill some valence bands? And that interaction is basically just a projection into the bands, below the gap, so because you fill it up with holes. So one can obtain the same interaction scheme here, which would be just projecting into these bands. You take the interaction. Now you can't project it just to this flat band. There's no way to do this because this flat band has gapless bands close to it. This is the folded band of this. Okay? So this flat band, you can't just project to this flat band. So what you have to project is you project, interaction, I don't know, 30 milli-electron volts, maybe even 30, right? Roughly. So you take bands within plus minus 30 here. There's nothing plus minus 30. You have to go to 60, and you just project into these bands. Now what you can clearly see is that if this gap would be small, that would be the wrong thing to do because you couldn't just project into the conduction bands, like in graphene, if the gap would be small. So there's another interaction scheme which is used in graphene, in single-layer graphene and twisted bilayer, where you basically subtract the potential or take into account, I don't have really time to go through it, but take into account the potential of the valence bands in the interacting picture, in the interactions. So you don't project, in the end you project into these bands, but basically because the density-density interaction is not just density of these bands times density of these bands, but it's a density-density interaction normal order with respect to the particle hole symmetric point. You basically subtract the energy, the density of the valence bands, and that creates a potential that basically fills the moire. It would be basically a potential that is created by these valence band states interacting. They're basically, which these valence bands basically fill the moire, so they would create a potential that basically influences these conduction bands. And the difference between these interactions is this delta rho here. This delta rho, you can, take this delta rho to be just either the rho of the conduction bands or to be rho minus 1/2, which is basically rho minus the charges of the valence bands, roughly. Okay? So those are these two different interaction schemes. One of them is used in twisted bilayer and in graphene, which are gapless systems. The other one is used if this gap was super large, because if I have these electron volts, then I would think that these bands shouldn't matter. Okay? So in these two interaction schemes, one of them really doesn't fill the moire, and that is this, just the projection into these bands. Why? The density-density interaction of these bands. Why? Because these bands at single particle don't fill them. The moire is 0.1% change. So these bands are basically, they don't fill the moire. Then the interaction doesn't fill the moire. So that scheme where you take the single particle Hamiltonian of these bands plus the Coulomb interaction only of these bands without any background subtraction doesn't fill the moire at all. The other way of doing the interaction, which we call average scheme, basically takes into account the influence through the density-density term in the interaction of the valence bands on these conduction bands. And the valence bands have the moire, so they will affect, the moire will become more important, and they'll affect the moire, they'll affect the valence bands in an interacting way rather than valence bands at single particle are never affected by the moire because the conduction bands at single particle are never affected by the moire because they're far away. So the valence bands can affect the conduction bands through interactions if you take a subtraction scheme in the density where you subtract 1/2, which is basically the charge at energy 0. So one of them, we call it charge neutrality scheme. Moire is less important. The other, we call it average scheme, where the moire is important. Any questions?
So how do you like, like, you seem to have like two schemes and you're sort of adding them both together?
No, so we just, no, so we do calculation with both of these schemes. So choosing which scheme you work on, this is actually a, long-standing issue in many body, at least in gapless systems, etc., right? So, we don't know, one might be overestimating, certainly one is underestimating. If this gap is small, there's no way this can be correct. But, you can say, oh, well, this gap is a little bit larger, then, this could be correct. So certainly you can say, oh, this one could be correct at this gap, at this, 60 milli-electron volts gaps. We don't know. Normally, there is some procedure to do these things, and this procedure is something that Kang and Wafek basically did early on by, doing some, starting with an interaction that looks like this, okay? Because this, by the way, this interaction, which you do subtract the valence charge background, that interaction is actually the one that respects the symmetries at zero field, respects particle, hole, etc. This other interaction doesn't. So you can start with that interaction and ask what happens in the RG. And you can ask, do I flow more to this or do I stay here?
And can you smooth slowly?
Well, we don't know. That's a calculation that's being done as we speak. Okay. We don't know what happens.
Okay.
I think in twisted bilayer, I think Wafek showed that basically you basically stay in this scheme if you start. But which scheme you choose is, at this point, unknown. And so we decided to do calculations with both of them, both schemes, and see the differences.
Okay, but the bilayer scheme that Wafek had, that had Moire, right?
I mean, that had Moire in the single particle, because that was for twisted bilayer.
Okay.
But, it doesn't really matter, because basically this interaction scheme also appears just in single layer graphene. This issue appears in single layer graphene also, because you're sitting at the Dirac node, and you must choose whether to subtract the background or not.
Okay.
So that's something this problem with choosing the interaction is inherent even in wireless systems. Okay, more questions? Okay, and this is Eves and Jabin's work, actually. So what you do, and this is how, you answer the question is, what does the moire do? So this is for the average scheme, which means the moire is felt by the conduction band, but only through the interaction with the background of the valence bands. This is for the moire, this is not felt by the conduction bands at all, even through the interaction. And what you see is similar looking plots. So this is Hartree-Fock, first of all. So, Hartree-Fock, what Hartree-Fock does is it takes the band structure, this gapless band structure, here in the valence bands, it folds it, so it'll fold it, it'll do like this type of, whatever, 3 and, this type of situation. This is the Moire-Briand zone. Okay? And then it will open gaps at the folding points, because that's what Hartree-Fock likes to do. And in fact, in both schemes, the charge, this is the charge spectrum. So charge Hartree-Fock is not the collective mode spectrum, just the basically single particle spectrum, Hartree-Fock spectrum, looks like now I've opened a gap. I've gotten a flat band. I've got a flat band. And this band is quasi-flat and has Chern number 1. Because if I have a gap band, it has to have integer Chern number. And the reason why I'm not plotting 2 of these is because this looks pretty much the same no matter which scheme you choose. So even if I don't have Moire, it still looks the same, right? And then you can kind of see some, this is, there's some phase diagrams, interaction, and displacement field. So at positive displacement field, you can see you go through a metal, churn 0, churn 1 state, metal. Okay, so this phase diagram seems to match the experiment. There's some different, things with the charge neutrality scheme, but basically it's the same thing. You get some, charge neutrality scheme cannot be trusted a small displacement field because that's just gapless. So, but if I go to some sizable displacement field, you get churn 1 also, which kind of seems to match. Don't read this side of this. Kind of seems to match what's shown, right? Churn 0, metal, churn 0, churn 1, metal state. You can see metal, churn 0, churn 1, metal. So now, what we can ask is since the single particle spectrum looks the same in both of these cases, one of them is 0 moire, absolutely. So you can ask, why did you fold to that moire length scale? Why didn't you fold to half of that, for example? Or any other thing. One of them does care about the moire. So we can ask, what's the difference between these two? Let's see. Let me just go. Okay, and the difference is obviously the only difference that can be is in the collective mode spectrum. And this you can see clearly here. Let me just walk you through these plots. You can first of all see here, don't look at this, look at these ones. These are charge plots, okay? Charge, Hartree-Fock charge plots. And you can see that basically they're very similar. So what are they? Well, one of them is this average scheme, which takes into account moire through the background of the valence bands, which are affected by moire. The other one is the charge neutrality scheme, which basically is identical almost to 0 moire. Okay? And here, in both schemes, what we can do is turn off moire by hand. And this KHBN is the turning off of moire by hand. Okay, so we go between 0, no moire. In both schemes, we can do that, right? By hand. Of course, at 0 moire, I shouldn't expect to have moire in either scheme because it's 0 moire. But at 1 moire, I should expect to have some moire effects in this average scheme, less in the charge neutrality scheme, in this scheme where I project, I should have moire effects to 0.1 milli-electron volts, which is really kind of very, very tiny, which is because the conduction bands are far away. So these are the spectra, charge spectra you see, they look very similar. Either you have moire, you don't have moire, or you have moire, very, very similar. You don't have moire, you have moire in the other scheme, very, very, you can't really tell the difference. There are some differences, of course, in some of the other bands. But for this flat band here, which is churn number 1 in all cases, there's not much difference. But one of them, which is this charge neutrality scheme, feels no moire. The bands have no moire. So what state is that? Well, that state is what's now called anomalous Hall crystal, but basically it's just a simple it's just a Wigner crystal, okay, with Hall conductance. And that's where the moire is not important, either in the interaction or in the single particle states. And then my folding is arbitrary. So I can say, I'm going to fold at some, and I can fold here, but I can also fold here, I can also fold here. I'm going to open gaps and spontaneously break translational symmetry in that case, because the moire is not important. So if moire is not important, I don't have, explicit translational breaking symmetry, but I have spontaneous, and that's a Wigner crystal. And this Wigner crystal, of course, should have gapless modes, which are the phonons. And this is what's plotted here. These are the gapless modes of the Wigner crystal, which Yves Jabin and Jonah and other Nicolas computed, basically, So Eve plots here there's many collective modes, okay, because there's some spin waves, forget about them. This is the zero momentum energy of the collective mode. So these are some spin waves, they stay because the system is polarized, so they're going to stay zero. Look at the x's. The x's are the phonons, okay? And you can see that, of course, when I have zero moire, there's no moire. This has to be a Wigner crystal. When I just turned off the moire by hand, this is the parameter that turns off the moire by hand. It's a Wigner crystal in both cases. But then as I turn on the moire onto the experimental values, basically this scheme where the moire is basically irrelevant shows you that this mode is barely gapped. Right? So it's still like a phonon. So whereas in this other scheme where the moire is important through the interaction between the conduction bands, which single particle have no moire, and the valence bands, which are affected by the moire, the phonon mode of the Wigner crystal shoots up dramatically and gets a gap. This is the difference is only in the, it's not in the charge spectrum. You can see it here. It's only in the collective mode spectrum. One is a spontaneous Wigner crystal, the other one. This is basically a whole, we call them anomalous Hall crystal these days, but this one is a moire churn insulator because the moire is actually comes in and you can see a sizable gap of these phonon modes. Questions?
So for this anomalous Hall crystal state, you say it's like a Wigner crystal. And like in my mind, there is like these two, the CDW and the Laughlin-like state. They are two different competing states.
This is an integer filling. So this is not.
Oh.
This is an integer filling of this band, right? So this is not at fractional fillings.
I
So
see.
this is a Slater determinant.
Okay, so far.
So far, it's Slater determinants.
Okay, are you gonna go to the fractional fillings next?
Yes, very soon. Next
Okay.
slide.
All right, I'll ask them.
Okay. More questions?
I have a very general question about band folding.
Yeah.
So when you break time reversal symmetry, you can say, is it weakly broken, is it strongly broken? For example, in a quantum anomalous Hall system, depending upon how strongly time reversal is broken, you can get small gaps or slightly larger gaps of your Dirac cones.
Right.
So there's some quantitative measure of how much time reversal symmetry. It's a strange thing to say, it's a symmetry, but still there's some quantitative measure.
Yeah.
Here, is there a similar quantitative measure of how much band folding you can have, and what does that actually physically mean? Does it mean that how much of the replica you see
But-
in the other zone?
Okay,
or-
very good point. So first of all, the time reversal breaking doesn't have anything to do with the band folding.
No, here, no.
Right.
I'm
So
giving you an
yeah.
example.
So here, these are basically, if I'm not mistaken, and Eve can correct me, but because they're his plots, but I don't think I'm mistaken. Basically, these is the other band. Okay, so you can see that the other flavor. Right? So you can see the symmetry breaking scale. This is the. It's larger than the Wigner scale. The Wigner scale is about half or a third of the symmetry breaking scale. So we flavor polarize the system, and that comes out. It's not that we did it by hand. In Hartree-Fock, it comes out. That's the Hartree-Fock that I would trust. The polarization of the system, because the flat band ferromagnetism, and we all know, or at least we think we know what it does, but actually in flat band ferromagnetism with projected Hamiltonians, there's exact solutions. Except this guy has some gapless modes. You know, Eretz had a paper where he showed that, you know, if this flat band with gapless modes, there's flavors, it still polarizes. In his paper, the wave functions were trivial, so we don't know what it does with non-trivial wave functions, but it's going to basically do the same thing. That's the Hartree-Fock that we would trust. The thing that's not that trustworthy is the Wigner crystallization, because we know Hartree-Fock gives you nonsense in most cases. Well, not saying nonsense, but it does give you It does give you things less trustworthy. So that's the Hartree-Fock that I wouldn't trust. But the time reversal, the basically flavor and time reversal breaking scale is basically this, which I would also look at it in the many-body spectrum. You can see the bound states. So you can see this is some spin wave. I could characterize the spin stiffness, although here there is just plotted at momentum 0, so we don't have, but I could characterize the spin stiffness of all these modes, and that's how I would characterize. I would say that in something that's spontaneously broken with time reversal, the right measure to characterize the strength of things would be the stiffness of the collective modes. That's what I would say. But I have to think more because I don't, but off the head, it's a very interesting question. So what I would say is the stiffness of the collective modes, but which I guess we have them if we want to get them. But yeah. Very good. More questions? Really? No more questions? Okay. Okay, so now let's say, we can say we sort of understand the nu equals 1 state. Basically, all the schemes give you the same answer, whether it's a spontaneously broken Wigner crystal or a Moiré-Chern insulator. The only difference is the gap of the phonon, of the translational symmetry breaking, very small gap in this scheme because there's almost no Moiré felt, larger gap in the scheme. And then at filling 1, this is what you get. You go here, this has Chern number 1. And we sort of understand why that has Chern number 1, but I don't have time to go into it. So now the thing that we completely don't understand is the fractional Chern insulator. So the initial papers on this, so I should be careful what I say since I'm on camera, but the initial papers, which were very fastly put out, were basically taken this band, this Hartree-Fock band, which was obtained at filling 1, and then sort of saying, well, I'm going to use this Hartree-Fock band, which is now gapped, okay, and it's got Chern number 1. And I'm going to use this band to then fractionally fill that band. Now, one should have problems with this for many, many reasons, but 2 problems that I think now are recognized by I guess, everyone are the following. First of all, this was the band obtained at filling 1, so I can't assume just a rigid, I'm going to fill this band. It's an interacting band because it's a Slater determinant, but I obtain it through interactions, through symmetry breaking, translational symmetry breaking. I wouldn't obtain it as single particle. So now I'm filling it to 1/3. Why should I assume it's just a rigid shift, right? We see a lot of things happen as a function of filling. Why should I assume? The second problem is this gap here, since it's Coulomb interactions cause the Wigner crystallization. This gap, as I showed you in both schemes, is of the order the interaction over 10, interaction over, right? So then if I project into this band and, go to fractionally filled and ask what happens with an interaction, well, that interaction that I'm putting in is still a Coulomb interaction, so it's going to have the same value as this gap. So you can't project it, right? It's like, or larger. This gap is 1/10 of the interaction or something, or not 1/10, but half or whatever. Anyways, the point is you can clearly not project here because you can't. A projection, as I'm a short Pivy showed, you basically have to have the interaction smaller than the gap between. This is exactly the opposite. It has to be the opposite because this gap, this band was formed by the interactions. There's no other. And the third thing is that, the third thing is the following. The system is, I showed you the band structure, right? The system here is gapless, for example, here, right? So if I really wanted to do an unbiased calculation, I should fill up this gapless set of bands at filling 1/3 and then turn on interactions and ask what happens. So let's see what happens in all those scenarios. Scenario number 1, I do the most biased thing, and I just project into this band and fractionally fill it at 1/3. Well, or 2/3. Well, we know what happens when you fractionally fill a Chern band. you get a fractional churn insulators. And this is exactly what you get, threefold degeneracy at filling 1/3, 2/3, doesn't matter. Any fractional filling you're going to put here, you're going to get a fractional churn insulator, basically. Okay? Small number of sites, you even get it. Okay? So these are Jabin, Jonas, and Eve's calculations, and Nicolas, basically, that basically you can clearly see threefold degeneracy, large gap to the next manifold of states. And by the way, the momentas are correct. These are fractional churn insulator states. But, you know, I just gave you 3 reasons why we really shouldn't trust this. Not why we shouldn't trust, why this is just, you know, it's not. Now there's talks at KITP basically saying this approximation is uncontrolled. It's actually very controlled towards biasing the system to FCI. So it's completely untrustworthy. And the problem is that if you want to do a better job, then you're basically out of luck. And the reason why you're out of luck is that you would need to take, you see here, at least at the K point, the K Moiré point, right? If I ask how many bands, what's the minimum number of bands that I need to take to do an unbiased calculation? Well, at the K point of Moiré, so this is the K Moiré point, I have, because it's the K point, I have at least 3 bands, okay? Because 3 bands fall there. It's the K point, I'm going to get 2 bands fold at the M point of the Moiré, 3 bands. So I at least need, the system is gapless with at least 2 bands, or at least 2 more bands here. Now, in order to do 3-band hexagonalization, you know, you can ask how many sites you can do. You can do 12 sites with 3 bands at filling 2/3, because that's, you know, whatever, 12. If I have 12 times 3 bands is filling 2/3 is 8 particles of the 12 sites. Filling 2/3 is 12 particles, but I have 3 bands, so my Hilbert space is 36. So 36 choose 8, that's doable. But this is the last number you can do. If you want to do 15 sites, that's not doable anymore. So you can do 12 sites, and if you do 12 sites, you get, if you do 12 sites, let me see if I have it. Well, this is the 3-band ED spectrum on, I think, 12 sites. Okay? If you see an FCI, then it's very clear there's no FCI here. Okay? So this is the on 12 sites. But what you can say, oh, you know, 12 sites is very, very small, especially for a system with correlation length, which should be large correlation length, because I have a gapless system. They say, how do you know I don't get FCI when you go to larger sizes? And that's the conundrum where we're in. The conundrum where we're in is that the calculations, the very simple calculations, which are projection, are controllably biasing the system towards getting FCI, and hence controllably unreliable. The other problem is that doing calculations with unrestricted, just diagonalization of 3 bands, because the Coulomb energy gets you, you know, you have to, the minimum number of bands you have to take is 3. I would argue this is, you know, sufficient because the Coulomb energy is around 30 milli-electron volts, so this is sufficient. But if you just do this unbiased, you get no FCI. So how do we explain the FCI, and does it, you know, the question is, yeah, the question is how do we explain it and what's really happening? Okay, so let me just tell you a couple of things which are, let me just show you. Hang on one second. I don't think I have enough time, but the problem is the following. One second. Okay, so let me show you how you actually can get to larger sizes here. So this, if you just do blindly 3-band ED, you're basically out of luck by 12 sites. You can't get anything meaningful there. But what you can do is some things that we devised, you know, over the extent of 8 months, which basically involve doing hexagonalization but in restricted Hilbert spaces. So when I fold this guy, I'm going to get 3 bands at the K point, 2 at the M point doing things. But there's still going to be a flat band, okay? I'm going to get gapless points, so I can't just neglect these. But these are dispersing massively because these basically have the velocity of graphene. So really, what I need to take into account is just this Coulomb, okay? So the first thing that you see is that you don't really need to sample the entire Hilbert space of 3 bands. Actually, plus all those 3 bands are actually connected to other bands, so you wouldn't be able to sample them at all fully. But basically, what the first trick to do to minimize your size of the Hilbert space, the trick that now you're trying to do is basically do calculations on a Hilbert space that's exploding for 3 bands massively. So the first thing that you can do is restrict the number of particles that you put in the dispersive bands. So you can see that basically I can say, well, let me say I have 24 particles. I have 24 sites. I want to fill up a third. These are the sizes we want to basically get to, okay? Roughly from 12, the fact that it goes exponentially, this is very good. So 24 sites at filling 2/3, I have what, 16 particles. I certainly cannot put 16 particles in 3 bands, which would mean 24 times 3. 72 to 216 would be, I think more than the particles in the universe or something. But basically, the Hilbert space. But basically what you can do is say, well, I'm going to restrict the number of particles that can go into the dispersive bands. Now, there's a minimal restriction because the bands are degenerate at these points, so you can't restrict it too much. Okay, but away from these points, you can say, I let the flat band, I allow the flat band to either be populated by all the particles or some fluctuations, but I only allow fluctuations in the dispersive bands made out of X number of particles. Okay, and that X you can put it to be 1, 2, 3, 4, 5, and see the evolution of the FCI with that number. So that's one thing you can do, and that's restricting your Hilbert space massively. The second thing you can do is you can say, well, I'm not going to allow some points of these bands, of these third bands, to be filled at all, and that's an orbital restriction. So for example, these points which are highly dispersive, even though they're in the third band, they're never going to be filled because they're further away from the Coulomb. So that's orbital plus particle restriction, and that basically kills your number of your Hilbert space dramatically. So you can actually go to 13 sites, and we do the following trick. So you go to 13 sites, and let me just see where's the slide. We go to 24 sites, and the following thing happens. So this is for the charge neutrality scheme. This tells you the number of particles that you allow in the first band, and not in the first band. This is the zeros band, this is the first band, this is the second band. I argue that you have to take at least 3 bands. Zeros band, first band, second band. The number of particles that you allow in the first band and the second band. If I allow 0 particles in the first band and the second band, I should just get the biased Hartree-Fock projection that you had before, right? So 0, 0 means I should get a perfect FCI. And this is what you get because 0, 0 basically means you're just not allowing any fluctuations into these bands, really, in a rotated basis. You're just you're fractionally filling this band, and that's it. So there you should get an FCI, and you get this FCI clearly here with a large gap. But then you add particles, you allow particle fluctuations into these other bands, and you can immediately see how your FCI gap collapses. Not only it collapses, but the momentum sector of the state changes. So for example, the FCI is not just this threefold degeneracy, but also the momentas. There's some momentas which are compatible with the gap state. Some momentas are not compatible with the gap state. There's just some Lieb-Mattis-Schulz theorem. So you can see the momentum changes at filling 2/3. So basically, the results, and I don't have time to go through them, right? I have 1 more minute? Wow. The results are that the two-thirds state disappears, at least in calculations, right? So it's not there, at least in calculations. Well, I should say that in the largest state-of-the-art ED calculations is not there. So then you can argue, well, we're not at large enough sizes. But you know, in a normal FCI, like the ones people were doing 11, 13 years ago, FCIs appear at 12 sites even. So 4 particles in 12 sites fitting 1/3, you see a nice FCI, right? At least in finite size. So, you know, if the FCIs will appear here at larger sizes, then why are they so prevalent at, you know, half a Kelvin? Why are they so strong in the experiment? That's one thing. So we either don't know, don't have the correct model, something is missing, but then this is graphene, so what is missing? Or the state is not there, and you know, I don't want to basically, this is the last slide. I don't want to, well, I don't want to claim that this explains it because it doesn't, because there's other states that are there that seem to remain. But basically, this is the data set 2, okay, which is, I guess, only posted a week or a week and a half ago. But basically, what this data set does is it goes from 500 millikelvin to 40 millikelvin. And what you see in RxY is that the RxY, which was 2/3, or well, RxY was 3/2, so sigma xy was 2/3, RxY was 3/2, 5/3. As you cool down the temperature, goes to RxY equals 1. So this, the 2/3 state disappears. The 3/5 state, you know, it still exists, or the 2/5 state, somewhere 3/5 state, it still exists at some, all the states, all the fractional states shrink, that's for sure. But some of them, this is Long's point, some of them still remain at some displacement field. Not all of them, but some of them still remain some displacement field. Now, there's no plot showing you, you know, the dependence of that region of displacement field for which the sum of FCIs remain with the temperature, which is really what we should get in order to see whether the FCIs will remain at 0 temperature. But the moral of the story is what happens as I cool down, as Long cools down the system, is that the FCI state, at least at 2/3, gets eaten by the Chern insulator state at filling 1. Okay, so the ground state at, you know, filling 2/3 is actually a Chern insulator at filling 1. Now, this eating of, you know, this cannibalizing of states of states is well known in fractional quantum Hall. So actually, early on in the days, Mansour Shayagan and other people basically showed that if you cool down some fractional states in quantum Hall, get eaten by the integer quantum Hall state. And that's basically some disorder, in that case, some disorder mechanism. Here, I don't know if it's disorder, certainly could be disorder. Certainly it could be that, as we showed, basically the 2/3 state, there's a twist. The 2/3 state is actually in the low energy manifold, we think, but not the ground state. The 1/3 state is clearly not, you know, clearly disappears faster. So there is, in theory, a difference between the states in calculations, but it could be that the 2/3 state is not the ground state anyways, somewhere in the low-lying part of the manifold, and then the states that are below it are more susceptible towards disorder, or they do something with disorder that's different, that would cause this, you know, cannibalizing of the 2/3 state by the nu equals 1 state. But all of these are obviously speculations, and doing a calculation now becomes even harder because now we know that somehow maybe disorder plays, well, clearly disorder has to play some role because you're cooling it down and things expand. For example, the Chern 0 state expands, the Chern 1 state expands, starts eating up the FCI states. So doing calculations with disorder interactions, when we can't do calculations even just with interactions, is going to be very, very difficult. So I think it's a very interesting time that requires new ideas, at least in the theoretical modeling of these systems. So maybe some more questions, and I'm done.
You said that the bias is basically doing a Hartree-Fock calculation for maybe like unit filling, and then assuming that we can fractionally fill that many-body state, the many-body flash band,
Yeah.
or doing an actual Hartree-Fock calculation with that filling factor.
Well, you can't, so you're not going to get the fractional churn insulators by doing Hartree-Fock. Never, you can't get a fractional quantum Hall state by doing Hartree-Fock, because it's not a Slater determinant. So even if you do a Hartree-Fock calculation at some fractional filling, you're likely to get a CW. Well, almost very likely. So you can never get, so Hartree-Fock only gives you that, anything that's not a Slater determinant in the new basis, you're not going to get it by Hartree-Fock.
So about the last point, the fact that the flat band is well not completely flat and not like a Landau level, could this play a role similar to disorder?
Not particularly. I mean, at least in calculation-wise, the interaction is, larger than the dispersion. So, it could kill some states, right? But this localizing, I don't think, disorder localizes, right? So you're not going to get that from dispersion. So I don't see a scenario where that's possible. Maybe other people see. Maybe others can comment, but.
Maybe I missed your point, but you're interested in the three states on the bottom and then the gaps. So why do fluidity?
Why do what?
Fluidity. Why don't do something like Arnoldi? I mean, just for the size of the space.
Oh no, you're still doing Arnoldi to get the ground state. You're still doing Langshos to get the ground state. But the question is, which Hilbert space are you going to use? To do the everything is Langshos. You can't do it's still exact diagonalization because Langshos is exact. 10 to the minus 14. It's exact.
But so the problem is storing the Hamiltonian?
Well, the problem, of course, the problem is first of all storing the Hamiltonian. You can't store 72 choose 24.
So you cannot construct it on the fly.
No, I mean there's matrix elements. For just plug in this binomial number in Mathematica, and it's just huge. and then even diagonalizing a matrix, right? The upper size is, I don't know, 2 billion. You know number 2 billion. Well, yeah, I mean hundreds of million. Nicolas does hundreds of million, for lunch. But you can push it to 2. I think we can push it 1 billion or something, right? Beyond that is even diagonalization. You can't do it. So you can't do 15 sites. Well, Monte Carlo. I don't know that Monte Carlo ever gave fractional quantum Hall. We got the expert on quantum Monte Carlo here. A sign problem. So, I mean, Monte Carlo is exact also, right? They're exact methods, but you always run into an issue. And exact diagonalization is the preferred method to get fractional quantum Hall, because that's so. You can think about DMRG. That could be a method, but there's people who know DMRG better than I do. So much better. So I'm not the expert on that.
In these schemes, do you ever get correlated hopping? Because you can cook up things so that correlated hopping helps you. I mean, they're like the old FCI papers that you're alluding to. So.
Right. So I think once you project, right, so the density is density, with or without subtraction. Once you project to these bands, you're gonna very likely get correlated hoppings because just the form factors, the way functions of the, but you know, at least in the model with our moire, we now think we have a Hamiltonian, and you know we can talk offline, but or Eve can tell you, but you know it's not yet flushed out. We now think we have a Hamiltonian that can tell you, and that one doesn't have correlated hopping, right? So in general, you probably do, but you know, in the end, yeah, let's talk offline about it because I'm not prepared to like. But it's basically, the problem is actually very simple, but with a very complicated, like nothing that you do matches the experiment, and then the experiment, you know, cools down and some states disappear, so then you're like, you know, so it seems to match somehow, because we don't find a two-thirds state, but then there's disorder, so it's a complicated thing, so it would be good if one could get to like a simpler model that one can, you know, it would be good if one could solve this gapless model with some correlated hopping and get some pair hopping or whatever and get an FCI. But it would have to be, you know, it would have to be a solid proof, right? Because otherwise you run into this, Hilbert space size. So you have to be an exact solution, for example. So if you find a Haldane pseudopotential for this, then that's, but short of that, it's okay, thanks.
Okay. More questions? Okay, since the microphone is here, one here and then one there, and it depends on you how long you want to continue.
Just really very quick. So you understand everything in the TMD scenario?
No.
No.
So in the TMD scenario, the TMD scenario is also very interesting because there's a lot of theory just being pumped out, which is basically contradictory with, you know. So the TMD scenario, there's many states we don't understand. So for example, we know for sure there's something interesting at filling -3 at low angle. This is Kim Feismack and G.S. Shan's fractional topological insulator. Now, the theoretical evidence for fractional topological insulator at that filling is 0. And you cannot get, what you get when you do a calculation, you don't get it. What we do understand in the TMDs and what can be reproduced, even including band mixing, so you know, really doing a solid calculation, is the state at -2/3, the kind of Jane sequence, -2/3, and I'm not sure about -3/5 actually. If we did -2/3, we did band mixing, so we can, but -3/5 I think we only did projection, so we don't, I don't, even -2/3 is solid. And it matches the experiment. -1 is solid, matches the experiment. Those ones I would be willing to, the rest, you know, but if you talk, you know, if you talk to Xiaodong or look at his data, there's not much, you know, they don't see FCI states in the second Moire band at any angle so far. So, you know, there's clearly Pfi's and GS experiment with -3, there's something very interesting there. But I don't think, calculation-wise, there's no sign in an FTI if you do it correctly. Now, there's many calculations that get an FTI by just biasing the hell out of the system and then predicting. But there's no unbiased calculation that gives you an FTI at -3. There's certainly experimental evidence there's something very interesting there.
Okay.
Yeah. So I got a couple quick questions related to like that peculiar.
To what?
To that peculiar band structure where it's like flat and then it shoots up. So the first one where you were showing how you're picking this table of numbers that tells you how many particles you allow in the dispersive bands.
Yeah.
It looks like you were adding like one more at a time to one of the bands and keeping the other one always empty. Have you also tried like?
Yeah. So you keep. So what you say is I only allow one particle.
Yeah, it looks like
extra band,
1, 0, 2, 0, 4, 0.
Right, but I don't restrict the number of particles in the flat band. I cannot restrict the number. So it's not like I allow one particle in the upper band and n-1 particles in the lower band. No, I build a Hilbert space by allowing all the Hilbert space in the lower band to be sampled, but only one particle in the second and the third band, or two particles in the second and the third band, or three particles in the second and third band to be. There was the 1, 0, 1, 0, 2, 0, 3, 0 was 1, 2, 3 particles in the first band, in the first excited band. Then you can go to 1, 1, to one. So we did all that. I don't have, there's a 100-page paper. We did all that analysis.
And is it qualitatively the same? Or if you're like...
Well, fluctuations just kill all the FCI states. So qualitatively, everything gets killed.
Okay. And then I'm wondering if you can go to a regime where like the flat part of the band doesn't extend to the Brillouin zone, like maybe make 1/3 of the Moiré band flat, and then it shoots up somewhere inside the Brillouin zone.
Well, I mean, you see, basically, this is a scale that's given by God, okay? God gave you this scale because he gave you carbon, or she gave you, or somebody gave you carbon, and that's some T over, that's VF over. So you can't, you can't really, you got VF, you got T over, T perpendicular over VF. All of these are known numbers, this is set. So you can't really change that.
Okay, but then you can change the Moiré period?
Yeah, but that's the effect of the Moiré, first of all, is controversial. We don't know what it is. And any Moiré period, even zero twist, will still be basically the same order of magnitude. Zero twist is 10 nanometers, I think, and 0.7 twist is 14 nanometers. 0.7 degrees is 14 nanometers. So it's basically in the same, and this is 12 nanometers or something. Okay. Roughly in the same regime. So I don't see a way of making severely 1/3 of, unless we find another substrate. But yeah.
Thank you.
So Andrei will be here, so you can discuss further with him. Let's thank him, and then there will be an
answer. Yeah, just a short closure announcement. First, if you're going to the surf class, pay, show up. If not, Maya will hunt you down. So yeah, don't do that. You don't want that. Yeah, last thing, just thank you all for all your questions. It was great. I think you did a good job. I thank all the speakers for the nice talks. And so let's just thank everyone and the guys at the back who do a great job for us. And now, yeah, let's go for lunch.
And thank you for the organizers.